right, so to continue where we were last time, we were introducing loops and repetition control structures. And I wanted to show you another tool to understand this a little bit better. It's called Python Tutor. Even though it's called Python Tutor, it's for lots of different languages here. It allows you to visualize and walk through your code. Now, this is not an everyday tool, but for beginning and for instruction, it is a nice little tool that you can visualize things and look and see how things are working. I'm going to go ahead and step through this code. You'll see here that we've set up an integer n being 5 on line 3. And over here, what is a stack, what is a heap? We'll get to that later. But here we are in main, and here's the n. But is it initialized yet? No, that's why it's a question mark. Remember, the default value for any variable in C is undefined. That's why they put in a question mark here. There is no definition yet until we set it on line 3. There we go. Now it has a value of 5. Okay? Remember, we are online, so if you have any questions, go ahead and post to the YouTube live stream. Otherwise, we're going to go through this loop now. Now, remember that this initialization only happens on the before the first iteration. So when I hit next here, we're going to initialize I to 0. Okay? Now, I is less than n. Is that true? Yes, because 0 is strictly less than 5. So it ends up going into the loop, printing it out. Now, observe, only after we've printed it out and at the end of the loop does I++ take effect and we increment I. So I is now 1. Right? It goes from 0 to 1. At this point, I'll go ahead and continue. 0, 1, 2, 3, 4. Right? There we go. Now it's 4. 4 is still strictly less than 5. And so when I hit next, it will print out 4. But now it'll increment to 5. And unfortunately, we don't get to see that because of the scoping rules that we talked about. Because I declared I inside this for loop, it is only good inside that for loop. So now that I'm outside that for loop, I no longer see it. Let's go ahead and edit this code to change the scope of the variable I. Well, first of all, let me show you that it is indeed out of scope. If I try to print it out after this loop, it's not even going to compile, right? Error. Scroll down to see your error. It's right here. I is undeclared. I does not exist as far as this program is concerned on line 7 because it only existed in the scope of this for loop. Let me change that. Int I. I'll just declare it right here. Right? And let me go ahead and get rid of this. There we go. Now let's go ahead and recompile this. Okay. And by the way, it's pythontutor.com if you want, and then you click on the C. But that's, again, it's not an everyday tool. It's if you need to understand how something's working, a small snippet of code, throw it in there and work it out. Right? So again, I'll fast forward here. We'll see that I is question mark as of line 5 because we haven't initialized it yet. Now, I will walk through the entire loop again. Right? 1, 2, 3, 4, 5, right, or 4. And now it will increment to 5. That's how we break out of the loop entirely. Right? You see now that it has a value of 5. We didn't see that before because after this loop, it no longer existed. It went away. Right? And so we now see that when I print this out after the for loop, it indeed is still 5. So why do it the first way? Why do it the way that I showed you to begin with? Basically, you want to limit the scope as much as possible, right? Yeah, here we go. The scope of a variable is its area of the code in which it exists, or it is valid. Excuse me. Best practice is to limit the scope of variables as much as possible. The reason for this is because you want to limit the number of potential failure points. Now, there's not necessarily anything going wrong in a program, but a program that has, like, say, 10 different failure points, it could fail at 10 different locations, right? It may never fail. It may pass, and it's good code. But if it has 10 potential failure points, that's a lot worse than having only, say, 5 potential failure points. So reducing the number of failure points, reducing the side effects, or reducing the scope of variables is a great practice to follow. Right? So this isn't great, that great code. In fact, this is old school C code. If you go into pedantic C code where you're from the 1970s or so, then you would have to do something like this. But at least in the last 35 years, you can do something like this, and you should do something like that. That's a proper loop right there. Okay? We've also seen some additional syntax here, right? And some other observations. The increment operator is done at the end of the loop. Right? Let me give myself some more room here so that it bounces up to the top automatically. There we go. Right? So that increment automatically executes at the end of a loop. Right? The I++ adds 1 to the variable I. Right? You may see ++I, which has the same effect, but a different value. And what I mean by that value is if you use this in an expression, you'll get a different value. One of them, the one on the top that I recommend is the postfix operation, plus I++. Just the opposite, ++I, is the prefix operation. Forget about it. Right? If you want to learn more about it, great, go ahead. But otherwise, I will only ever use the I++, just to limit the cognitive load that we've got for all of our values here. Right? You don't have to use it. But some other things are useful. If ++ adds 1, what do you think minus does? Subtracts 1 from the variable I. Right? Well, what if you want to do it with different values? Right? You could go with I + = 2. Right? This is equivalent to I is equal to I + 2. Right? There we go. I'll write it like that. Right? In other words, you can shorthand that. Instead of having to write I is equal to I + 2, an entire expression on the right-hand side, you can shorthand that with just simply plus equals. Okay? And that allows you to do things other than 1. Plus, minus, that only is add 1 or subtract 1. If you want to add 2, right, then you can use this, right? Adds 2 to the variable I. And it doesn't have to be 2. It could be 3, it could be 4, it could be 5. And yes, you can use them with doubles, although it's not that common. Right? You can use it with subtraction. Minus equals 3 subtracts 3 from I. Right? And unlike plus and minus only work for addition and subtraction, you can use I times equals, that's multiplication, 2. Doubles, or times 2, the value in I. Right? So it'll double I. You can also use I divided by equals 3. And the right-hand side, by the way, can be more than just a literal, just a number. It can be an entire expression. Although, again, that's not as readable as just a single number there. But you have to be careful about this, right? Divides I by 3 using integer division. What have we learned about integer division? If I had, say, example, what if I had I is equal to 10? Actually, no, let me go into full code mode over here, right? So int I is equal to 10. I divided by equals 3. Right, there we go. Printf I is equal to %d and the line I. What is this going to print? So we can do division in our head. 10 divided by 3 is what? 3.3333, but this is integers. What happens to that 0.33333? Chopped off, thrown away, truncation. So I'll end up with just 3. Right? 3.3333. It doesn't round up, it doesn't round down. It just takes that 0.3333, chops it off, and throws it away. Right? So you can use all of those with these. These are called compound assignment operators. Right? Many languages support them. C, C++, Java, even Python supports all of these. However, Python does not support the increment operators or the decrement operators for whatever reason. Right? Okay. Again, you can. It's best practice to limit the scope of things. Right? All right, that's for loops. Any questions on those so far? Yeah. So good question. The question was, can you use remainder? Let's find out. Right. My prediction is it will not even compile. Oh, it does. All right, my prediction was wrong. Let's find out what happens. So divide equals 3. The remainder would be 1. So if this is giving us the remainder, it's going to be 1. Otherwise, if it's giving us the division, then it's going to be 3 again. Looks like 1. Yes, you can. Right. It's weird. I've never actually seen somebody do that, but you could do that, I guess. Right? Gross, though. All right, well, we've got for loops. There's another loop control structure called while loops. Right? And the difference is, well, one of the key differences is while loops, guess what? Use the keyword while. Right? They are different than for loops. Let's just go ahead and get into it with an example here. If I want to count from 0 to 10 again, int n is equal to 10, right? Or 0 through 9, excuse me. Let's go ahead and go with that. A for loop to do that would be for int I is equal to 0, I is less than n, I plus plus. That's what I mean by the idiomatic for loop. You will get so used to writing a for loop like this over and over and over again that you won't even think about it. Right? I'm going to rewrite this as a while loop. Right? However, the three parts, the initialization, the continuation, and the increment are all done on different lines. Instead of all on this line and within this for and parentheses, they all get separated out. The initialization is done before the while loop. Right? The continuation is done in the parentheses. No semicolon in this case. And the continuation is done inside the while loop with a semicolon. There we go. And if I print this out, I will get the exact same behavior as before. I is equal to %d and the line. I. GCC, and run it. 0, it does begin at 0, all the way to 9. That's an equivalent while loop for the for loop that we were developing before. So why? Why do we have two different types of loops? Right? There's a non-trivial fact that you could say, take any for loop and translate it into a while loop. You can take any while loop and translate it into a for loop. So why do we need both? We could just get by with one. We could erase all of our ideas about while loops and do everything with for loops, or vice versa. Think about regular language, like regular natural language is what we call it. Right? English. Do we have just one word to describe good? Good, cool, awesome, neat, fantastic, right? Why do we have so many words to describe the same basic thing? It's to make the language richer, to make it more flexible, to make it more usable. Likewise, we have two scenarios in which we would generally use one loop over another loop. All you have to do is read it in your head. For this many iterations. Oh, I know how many iterations I'm going to go. While this condition is true, I don't know how many iterations I've got there. We'll formalize that here in a second. But before we do, let's make our observations about the differences with these while loops, or with this while loop, right? The difference is that all of the elements are separated. In fact, let me grab this and put it over in the notes so that we can just look at it. There we go. All right. So there's our while loop. All three elements are separated, right? In general, a while loop is a little bit more flexible, right? Why? Because you can have a bit more control over where the increment is placed. Increment. There we go. Increment is placed. For example, with a for loop, that plus plus is always done at the end of a for loop, as we observed over here in Python Tutor. Right? But what if I were to change that with a while loop? I'm doing that at the bottom with this initial version of it. What if I take that and move it up here? Oops. There we go. What if I do it at the beginning of the for loop? Let's think about this. Clear it. GCC it. And before I run this, let's walk through it without Python Tutor. We can do this by hand. Right? I has a value of 0. Okay. Is I strictly less than 10? Yep. So this executes. But before I even print it out, what do I do to it? Ding. Add 1. So what's the first value that actually gets printed? 1. What's the last value that's going to get printed? 10? Let's find out. 10 or 9? Right? Just roll the dice on that. Right? You have a better chance than the money line on the CU and U. Right? Anyway, don't gamble. It's bad. Anyway, why did we get 10 at the end? Because it was 9. Think about this. At some point, it gets to be 9, right? 9 is strictly less than 10, so we execute this while loop once more, the body of this while loop. What happens to that 9? First thing you do is you add 1. 10, and so you end up printing out 10. Now, what happens when we come back up here? Right? Is 10 strictly less than 10 again anymore? Nope. 10 is equal to 10. And so we end up breaking out of this while loop, and the value I has a value of, what if I print it out one last time after the loop is completely done? It's gone up to, oops. Oh, it's gone, it's still at 10, right? Because that's how we broke out of the while loop, excuse me, right? 10 is no longer strictly less than 10, so it has a value of 10 now, right? Even after the loop. And this also highlights another key difference between a for loop and a while loop. With a for loop, what did I do? I scoped it down to the loop itself. For int I equals 0. But now because I am making or declaring I before I even get there, guess what? I can't limit the scope. There is no way that you can do something like this. For int I is equal to 0. If I tried something like this, I'm pretty sure that this is a syntax error. Yeah, you can't do something like that. That it only takes this continuation condition in there. If you want something like this, you're shopping for a for loop instead. Right? Undo, undo, undo. There we go. Yeah. There. Right? So you have a little bit more control over how your loop behaves. Also, with a for loop, you can limit the scope of your iterator variable, or increment iterator slash increment variable. But with a while loop, you can't. Right? Maybe you do, maybe you want to, maybe you don't. Okay. So again, generally the initialization occurs before the loop. Right? The continuation is still bound to the while keyword. Right? As long as the continuation condition is true, the loop will execute at least one more time. Some other key syntax differences. Syntax. Right? There is no semicolon at the end of the continuation condition, like there was in the for loop. Right? We did not have a semicolon right here. Right? We did in a for loop, but we don't have it with a while loop. The loop body is still denoted with curly brackets, so there's no change there. Right? And again, remember, to kill a program, you use, what was it again? Control C. There we go. Okay. So once again, why do we want two different loop control structures? And by the way, there aren't just two. There's also a do while loop that I generally omit. The key difference there is that the loop will execute at least once, regardless of the continuation condition, and the continuation condition is checked at the end of the loop instead of at the beginning of the loop. Right? Again, I want to scope it down to just two. If you want to use do while loops, great, go ahead, make sure it works. Right? But I won't be covering them generally. Right? So again, you can take any for loop and rewrite it as a while loop, or vice versa. Take a while loop and rewrite it as a for loop. You don't need either one. In general, use a for loop when you know up front how many iterations, either say 10 iterations or n iterations, you will execute the loop for. Right? Use a while loop when you don't know how many iterations it will go. Instead, it depends on a value or variable or some other condition. Right? Here's the example that I'm going to give you. Write a program to compute the number of digits in an integer. Right? So how are we going to do this? You're going to help me out. Right? First of all, I'm going to come over here and I'm just going to declare integer n here to be 1, 2, 3, 4. Right? Well, how many digits does that number have? 4. Why? How did you know that? Because you look at it and say, you can see 4 digits. Because I did 1, 2, 3, 4, right? On purpose. How many digits does 1, 2, 3 have? 3. How many digits does n have if I were to read it in from a user? a to I of argv sub 1. How many digits does that have? They could enter 1, 2, 3. They could enter 1, 2, 3, 4. They could enter negative 10. Right? Negative 10 has how many digits? 2. We don't count the negative sign. 0 has how many digits? That's a good question. 1, 0. Right? So it's not 0 digits because you actually write something. You write down 0. Right? All right, so how many digits do I have? Well, I do actually want a test case here. So I'm going to go ahead and hard code this to 1, 2, 3, 4. And we're going to develop our algorithm here. Right? Now, I don't have a nice whiteboard. I could have brought my iPad or something and we could have whiteboarded this. But that's why we have whiteboards. In fact, we call the act of writing a solution up on or a potential solution up on a whiteboard called whiteboarding, right? You whiteboard your solution or you take out a piece of paper and you start writing things down, right? I don't have a piece of paper, so I'm going to outline it here in what we call pseudocode. Right? So does anybody have any ideas? I'm going to write it out in pseudocode using comments here. I'm going to outline my program here. Anybody have any ideas? Here, I'll give you a hint. Oh, yeah, go ahead. Okay. Yeah. Okay, divide. I like that idea. Divide it by what? What if I divided it by 10? What number will that become? 1, 2, 3, 4, 0.4, but if we use integer division, it will end up becoming what? 1, 2, 3. I divided it once to get rid of 1 digit and corresponding to 1 digit. What if I did that again? 1, 2, 3 divided by 10. That will give me what? 12.3, and that gets truncated to 12. Right? What if I did it one more time? 12 divided by 10 is going to give me 1.2. Again, truncation is going to give me 1. One more time. 1 divided by 10 is going to give me 0.1, which gives me 0 after truncation. So if I just did this over and over and over again until I got down to 0, or flip that, right? Because that's a termination condition. You stop when you get to 0. So when do you not stop? When do you continue? When you're greater than 0. So while, and by the way, this is not pseudocode here. This is just one example. Always start with a concrete example and then generalize it. Right? Go back and say, okay, well now this is n. N divided by 10. So while n is greater than 0, do the following. Divide n by 10, relying on integer truncation. Right? And then I should also make sure that I have a counter here to count how many times I did this. Right? So increment a counter for the number of digits. There's my outline. This is not real code, right? This looks kind of like Python, but it's definitely not Python. There's no programming language like this. That's why we call it pseudocode. Pseudo stands for fake. It's fake code. It's just an outline, right? And by the way, should any of this stuff be in your final submission? No. Again, if I were doing this, I would not be doing this in on IDE like this. I would be doing it on the whiteboard or on a piece of paper if I were working alone, right? Okay, let's translate that pseudocode to C code. While n is greater than 0. There we go. That's a pretty direct translation there, right? Divide n by 10. N is equal to n divided by 10. Is there a better way, quicker way that I can write that? Divide equals 10, right? And then increment a counter for the number of digits. So I could say number of digits is equal to number of digits plus 1. Again, is there a better way? Or not better. I'm not going to make a value judgment on it. It's just quicker. And once you get used to it, it's also quicker to read it and therefore quicker to understand it. We use the word grok. Have you ever heard of that before? If you're a science fiction reader, grok, G-R-O-K, is to understand something intuitively and immediately. Right? Once you get used to this syntax, plus, 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 you'll grok it right away. You'll see it, you'll understand what it's doing. You'll never have to think about it once you get used to it. Right? All right, that's a pretty good, translation there. So printf, %d has %d digits. Right? I'm going to print out n has num digits. Okay, and of course I can't have question mark here. Where should I start my counter? Where did I start it up here? There's 1, 2, 3, 4. Oh, it has 4 digits. So therefore I should have started it at 0. Okay. I'll leave that for now because we might need to come back to it. Right. 0 has 4 digits. Bug number 1. First of all, this is not a bug, it's just a bad formatting issue. But bug number 1. 0 has 4 digits. Well, of course, n is what value at this point after the while loop? 0. So if you want to modify n but preserve the original value, you're not paying by the variable. Just go ahead and give yourself another variable. Original value, right, is equal to n. Now instead of printing n down here, which by this point is just 0, that's how I got out of the loop, I will go ahead and put the original value here. There we go. There, 1, 2, 3, 4 has 4 digits. Is everybody 100% convinced that this is a bug-free program just by looking at one example? I'm not. Let's change it to 1, 2, 3. Now are you twice as convinced that it's correct? Okay. 1, 2, 3, 4, 5, 6, 7, 8. Now are you even more convinced? Maybe it's just because it's 1, 2, 3, 4, 5, 6, 7, 8, right? What if I did 4, 4, 4, 4? 4 fours, right? Maybe I was just getting luckier. That it's something about the number that, well, it works. Are you convinced now that it is correct? I tried like 5, 6, 7 numbers, right? No, that's not the point of testing. The point of testing is to give you a high degree of certainty that the code is correct. In fact, what I'm doing here is what's called ad hoc testing. Right? I'm just doing a sanity check of, well, here's one number, here's one number, here's one number. Right? What kind of numbers have I not tested yet? Negative 1, 2, 3. What should the answer be there? 3. No digits? All right, so negative 1, 2, 3. Does this while loop even execute? No, because negative 123, is that strictly greater than 0? Nope. It doesn't even execute. And so we end up with the original value of num digits. All right, fix it. Oh, okay, I could take an absolute value. While the absolute value of n is greater than n. Some people have been exploring the math library. Awesome. What else might help you going forward in the math library? Round, right? You can round numbers to the nearest whole number. We'll talk about that later. But you do have to be careful here. This will work because I'm working with an integer, right? If I had a double, pi is equal to negative 3.14. There we go. Printf, the absolute value of pi is %f. There we go. End the line. And then abs of pi. Oh, by the way, I'm just doing this out of convenience because I can't use the math library pi. But one thing that we were seeing all over the place is that folks were defining their own pi. And then they were not getting the correct numbers because their pi was only out to 2 decimals or something. What should I have been using here instead? The math library, right? m_pi. But let me go ahead and try to print this out. Yeah, that's just a warning. Don't worry about it. There we go. The absolute value of pi is, okay, 0? Nope. What is going on here? There's an absolute, if you read the math library, in fact, let's pull it up. See math.h. I'm RTMing here. That's a great acronym. Read the manual, and then you can emphasize it by saying RTFM, right? And you can understand what F is standing there for, right? So, absolute value. Let's take a look at the absolute value. Computes the absolute value of this. There's also a fabs up there. I wonder what that's for, right? absolute value. Ooh, this is C. This is C++. Darn it. All right, let's go ahead and look up the manual pages for this one. Man abs. There we go. Oh, there is no manual. Okay. C math.h abs. There we go. Maybe this is it. Okay. It's saying it's a long. A long is an integer. In other words, abs is for integers, right? If you want to operate on doubles, what do you need? Fabs. What is that F standing for in front of it? Floating point numbers. Right? All right, now let's go ahead and bring this in. There we go. There. Now it works. Right? Because it wasn't performing integer truncation. Okay? So keep that in mind as you are looking at the math library. Just like you had to in your hack, right? Sine, cosine, tangent, arcsine. They didn't operate on degrees, right? They operated on the proper scientific way of operating on things, which is radians. Right? Okay, so I just got rid of that. That was just an aside. 1, 2, 3, negative 1, 2, 3 has 3 digits. What about all that other stuff that I just tested, though? I made a change to my code. How do I know that that stuff still works? Right? I don't. That's the shortcoming of ad hoc testing. I don't know if I've regressed. In other words, if you've got like 99 tests or 100 tests, 99 of them are passing, but there's one test that's failing. You go and you fix that test. How do you know that by fixing that test, now all the other 99 cases are now failing? Right? That's called regression testing. Right? And if you have a proper unit testing framework, which we'll get into after the exam, then you don't have to do any of this stuff. Once you write code, you write the, or some people want to do it backwards and write the, that's called test-driven development. You write the tests, then you write the code, and you see if it passes. We're going to write the code, write the tests, and see if it passes. The code, the tests is also code, just like you saw in your lab last week or this week, I forget, where we set up some informal unit tests for the leap year, right? And once you go back and fix the leap year, all you have to do is recompile, run it again, run it again, run it again as many times as you want. Right? Every time you change the code, run it again to see if you screwed up some other tests. Right? Rather than having to change it, try it again, change it, try it again, change it, try it again. Right? I'm still not satisfied though. So if you're in calc class, right, and functions sometimes blow up. For example, if I said 1 divided by n, right? Or 1 divided by x, because you always use x on the x-axis. Is that a continuous function everywhere? Don't worry if you don't have calculus. What happens at one discontinuous point? In particular, that discontinuous point is 0. It blows up. Right? So does this blow up when we've got that weird edge case? We call these edge cases or corner cases, right? They only happen at the very edge of things, right? They're not the norm, right? We're not always going to have 0 here. There's only one 0, but there are many other positive values. There are many other negative values, right? Right? Let's see what happens. Is that true? 0 has 0 digits? No. So I'm going to go ahead and erase all this now and look again. One of the ideas with loops is that sometimes you can't just write a loop for everything. Sometimes there's one case where the loop doesn't apply. Sometimes you've got, you can go into a loop and handle everything with the same except for the first iteration, and you need to handle that differently. Or you can handle everything the same except for the last iteration, and you need to handle that separately. Right? In those cases, you know, you write the loop for the general case, but then you take care of those specific instances. So for example, I don't want to have to deal with that. If n is equal to 0, then I will print out a different special message just for that one value. Printf 0 has 1 digit. Right? I'll just hard code it. Right? Who cares? And then I'll put everything else into an else statement here. Right? And all of my indentation at this point is way off. Right? So go back and manually change. Remember, what tool did I show you that you could use to get it done automatically? A style. Right? Demo.c, there we go. And it reformats it all for me. Oh, nice. Right? We were seeing, not frequently, but we were seeing folks that didn't have any indentation at all, that had indentation all over the place. Right? If you get your program to a point where the indentation is all screwed up, run A style, but get into the habit of writing correctly to begin with. Right? All right, nice. Now, does that take care of my one problem? Yep. Now we can go ahead and change this to the most general case, A to I. I don't have to do this ad hoc anymore. I can go ahead and read this in as a command line argument. There we go. Run that. Provide 1, 2, 3 at the command line. Oops. ECC demo. There we go. A dot out. 1, 2, 3. There we go. 1, 2, 3 has 3 digits. Now it's way faster, right? I can go ahead and put on whatever I want at the command line. Right? 7 digits. It all looks good to me. Right? And it can be tested a lot quicker. Right? Except that there's another condition I could have here. Yeah. Oh, okay, yeah. I could mash the keyboard. Right? Is that going to work? No, 2.147 billion is the biggest number. It'll probably work here. It'll fail to actually get that entire number. It'll give me some number. Yeah, -1 because of overflow. But it's right. -1 does have 1 digit. Right? What if I did something like this, though? I don't give it a number at all. I'm about to hit enter. Segmentation fault, core dump. Okay? So what could I have done to prevent this? I could check. Did you give me enough command line arguments? If argc is the number of command line arguments. If that's not equal to some number, then I can say printf, error, you need to provide an integer. Or some helpful message here. And then I'll exit the program gracefully with a 1. We'll talk about what that means later, though. All right? What's that question mark there? 2. Why 2? What's the first command line argument always provided? The executable file name a.out in this case. So if I'm looking for one user-provided command line argument, then I'm looking at 1 over here, 1 of the original, and so I need 2. So if it's not 2, error, you need to provide an integer. Okay, fine. 1, 2, 3, 1, 2, 3. I provided how many? 3 command line arguments now, and I will have an error. Only when I am a good user and I follow the instructions that my program has given me does it actually succeed. And negative values still work. 0 still works. What else could go wrong? Yeah, not a number. Not a number. Or hello. Now before I execute this, you do have to think about the worst type of user, the ID10T user. Right? You ever heard of the ID10T user? The idiot, right? So to make our code in ID10T user proof, right? Hello is 0? Okay. How do we take care of that? Why? Well, first of all, let's understand why it's 0. Right? So A to I is going to process hello. Right? It sees H as the first character. Is that a number? No. So it stops and says, what have I parsed so far? What have I looked at so far? Nothing. So therefore, what's the numerical value of nothing? 0. And that's why we're getting 0 here. We're not going to worry about that too much, but you should be thinking about this, right? And all of our test cases, we will throw bad values at you occasionally. For example, 1, 2, 3, 1, 2, 3. Did you check for the correct number of command line arguments? But we're probably not going to give you this egregious of a bad input. Right? We could give you bad inputs. For example, if you expect a positive integer, and we give you a negative integer, you should be able to check for that. And things of that nature. But now that we have conditionals, checking for command line arguments, at least the correct number and the correct type, those are perfectly valid. Right? All right. I really like this. I'm done. Right? I'm convinced Even though I don't have proper unit testing here, I'm convinced that this is correct. Right. There you go. It's in your notes. Now, that entire detour, why did we do it? Again, when do we use a for loop? When do we use a while loop? I think it was your suggestion over there that that we would do immediately you jump to a while loop. Why did you immediately jump to a while loop? 1, 2, 3, 4 has 4 digits. Did you know that up front? No. Well, I mean, you did by looking at it. But if you knew how many digits you had, would you need to write a loop at all? No. So you did not know how many iterations up front that it would go. Otherwise, if you did, then you'd be done. You wouldn't need a loop at all. And by the way, there's a way to do this without a loop. The logarithm base 10. What are logarithms? They're the inverse of exponents. So that gives you the number of digits in a number, right? Logarithm base 10. Base e is the natural logarithm. Base 2 is the binary logarithm. But there is a way to do it with just a one-liner. Right? All right. But I didn't want to get into math. Right? Okay. So you can have loops within loops. Right? There's an author, the book is called Gödel, Escher, and Bach by Hofstadter, I think it is. It's a big, giant tome. If you're getting to computer science theory in depth, I recommend it. It's a good read. And he calls these things strange loops. This is very apropos of AI now, right? Is ChatGPT 4.0? Is it sentient? Is it true artificial intelligence yet? Most people don't think it is yet, but it is giving people pause, right? It is passing the Turing test in a lot of people's minds. Philosophically, somebody like Hofstadter would have called that a strange loop, right? He characterizes human intelligence, human sentience, human awareness as a strange loop, that very simple neural networks in our brains, just a lot of them is what gives us our understanding, right? And so all these strange little loops that, now that there are billions of them, that's what's responsible for intelligence. That's what's responsible for sentience, right? And now we just have, I mean, that's what ChatGPT is, by the way. It's just a bunch of little loops. It's a neural network. It's just that we haven't had the giant, massive computing power until now to actually realize so many neurons. Right? Anyway, you can have a loop within a loop. That's not exactly a strange loop, but that popped a neuron in my head to think about that. Right? We refer to them as the inner loop and the outer loop, or the outer loop and the inner loop. You can do this as many times as you want, but try to avoid it as much as possible. So that's in your notes already. So let me show you a nested loop. And I'm just going to go with a for loop here. For int I equals 0, I is less than n, I plus plus. Right. There's our regular old loop. Int n is equal to 10. Here's our inner for loop. You can put whatever you want inside this loop body, including another loop. You can put a while loop in here too, mix and match. Kind of ugly, but int j, actually, could I do this? Could I go with I again? How many variables do I have that are named I now? 2. You can do this, but it's too confusing. So give me another variable name. J. Why did you jump to J? A, B, C, D, I, J, right? And if we did one more, it would be K, right? J, J, J. I won't go with 3. Right? Printf I, J is equal to %d, comma, %d. And I will end the line and print those, I and J. There we go. Tell me, how many things total is this going to print? Let's walk through it really briefly. So for I equals 0 up to n, so I is going to be 0. It will execute this inner for loop how many times? 10 times, printing out for j, running from 0 up to 9. Only after that's done will we come up here to the for loop, and now we're at 1. It'll print j, 0 to 9. I will then become 2. J is 0 to 9. J is 0 to 9. J is 0 to 9. J is 0 to the 9. How many things total will it end up printing? Count those up. Oh, what? Not everything. There we go. There's 0, 0, 0, 1, 0, 2, 0, 3, dot, 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 0, 9, 1, 0, 1, 1, 1, 2, 1, 3, dot, 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 2, 3, So if I execute this outer for loop 10 times, and each time I do, the inner for loop executes 10 times, how many times total? 10 times 10, 100. Int counter is equal to 0. Let's verify that. Counter plus plus. And then let's print the counter at the end. $100 times. What if I bump this up to 100? How many things is it going to print out now? 100 times 100. Call that 10,000. What if I went up to 1,000 thousands? We call them millions. That's a great line from Once Upon a Time in the Old West. Great 60s Western. Watch it. Right. So, should I sit here and wait for it? No. This is growing quadratically, right? If I've got n times n in general, then it's going to be n squared, right? In this case, it'll be a million, right? It executes, but whatever, right? What if I went up to 1, 2, 3? 1 million millions. What do we call them? Billion, trillions, right? Call them trillions, right? And it will run, but the counter will not be correct, but it's going to take a long time. In fact, I'm not even out of the 0 on JI yet, right? What does that tell you about loops like this? Nested loops. Be careful, right? Because a loop within a loop means that you are doing loop times loop n squared operations. Right? I'm going to kill this because it's not an infinite loop, but it is an extremely slow loop that we're not going to get through. Right? We got to 1. Yay! Right? While I was talking. So be careful. I'm going to bump this back down to just 10 and put it in your notes as an example. Right? So let's see. There we go. Right. But avoid this at all costs. Right? Certainly 3 or more nested loops. Really rethink what you are doing, right? Why? Because now I'm not n times n. Now I'm n times n times n. We don't call that quadratic anymore. We call that cubic, right? And now a million times a million times a million. That's not trillions anymore. That's what comes after trillions. Quadrillions. That's quintillions, right? Something, right? Yeah. Don't do that. When we come back on Monday, we'll talk about some common pitfalls. Guess how you can avoid those common pitfalls before I even show them to you? The wall flag, right? And there, now I'm getting that's for other reasons, but always remember the wall flag.